So today, let's think of ourselves as architects, but instead of buildings, we're designing the digital world. We're going to pull back the curtain on the blueprint that developers use to build the massive, complex software that, let's be honest, we all depend on every single day. Let's jump right in. I mean, really think about it. That app on your phone you use all the time. It's got dozens, maybe hundreds of features. It's getting updated constantly. And somehow it works for millions of people all at once. How on earth does a team of developers even start to build something like that? And yeah, that's the real question, isn't it? How do you manage all that complexity so it doesn't just collapse into a tangled, chaotic mess of code? Well, the answer lies in a really brilliant way of thinking about software design. And that approach is called object-oriented programming, or OOP for short. You see, instead of just writing one gigantic, long list of instructions, OOP is all about creating a structured blueprint. It's a way to organize your code into these logical, self-contained units that actually model things from the real world. And trust me, that makes everything so much easier to build, to manage, and to grow over time. Okay, so what are the absolute core pieces of this software blueprint? Well, it all boils down to two fundamental ideas: classes and objects. First up, we've got the class. Now, the best way to think of a class is as that architect's blueprint for a house. It defines all the essential stuff, how many rooms it has, the layout, where the doors go, but it's not the actual physical house itself. In the world of code, you might have a student class. That class would define properties like name and methods or actions like calculate grade. It sets the rules for what every single student you create is going to look like and what it can do. So if the class is the blueprint, then an object, well, that's the actual house you build from it. It's a specific, real thing. So using our student class blueprint, we could create tons of different student objects. We could have one for John, another one for Jane. Each of them has their own unique name and their own grades, but they all follow the same fundamental structure that was laid out in that student class. Now here's where things get really efficient. Great architects don't draw a brand new plan for every single house. No way. They reuse and adapt plans they've already made. In OOP, we have this incredibly powerful concept for doing the exact same thing, and it's called inheritance. Inheritance lets us create a new class. We'll call it a child that automatically gets or inherits all the features and behaviors of an existing parent class. This is an absolute game changer for code reusability. You define a general blueprint one time, and then you can create all sorts of specialized versions from it without starting from scratch. And this isn't a one-size-fits-all deal either. This idea can take a few different forms. You've got single inheritance, which is a straightforward parent-to-child relationship. Then there's multi-level, which is like a chain reaction where a new blueprint is based on another blueprint that was already modified. And finally, hierarchical, where you have one main blueprint that's used as a starting point for a whole bunch of different specialized children. Let's just quickly walk through that multi-level chain, because it really makes it click. You start with a base blueprint, right? Let's call it the grandparent class. Then, a parent class can inherit from that one, maybe adding a few new features of its own. And finally, a child class can inherit from that parent class, getting everything from both the parent and the grandparent, and becoming even more specialized. See how each step just builds on the last one? But wait a minute. What if that new, specialized child class needs to use a feature exactly as it was defined in the original parent's plan? Well, that's where the super keyword comes in. You can think of it like a special note on the new blueprint that says, hey, for this one thing, don't use my version. Go back and use the original master plan's version. It's a really handy way to reuse specific parts of the parent's design without having to rewrite them. All right. The next major pillar of our software blueprint is a concept that sounds pretty complicated, but I promise the idea behind it is super intuitive. It's called polymorphism. At its heart, it's simple. Polymorphism just means many forms. It's the idea that a single action can have a bunch of different outcomes, depending on the context. So, for example, the action move means something totally different for a car object than it does for a fish object, right? It's one name, move, but it takes many different forms. One common type is what we call runtime polymorphism, or method overriding. Just imagine you have a general animal blueprint with a method called makeSound. Now, a dog object inherits this, but it overrides that method to make a bark. A cat object also inherits it, but it overrides it to meow. It's the same method name, makeSound, but the specific behavior is decided when the program is actually running. And then you've got compile time polymorphism, or method overloading. This one happens inside a single class. You can have multiple methods with the exact same name, let's say add, as long as they take different inputs or parameters. So one add method might take 2 numbers, while another version takes 3 numbers. The system is smart enough to know which one you want to use based on the inputs you give it, even before the program runs. Okay, so let's put these two side by side because it's really easy to get them mixed up. The key difference is this. Overwriting is all about changing an inherited behavior in a child class, so it's happening across 2 different classes. Overloading, on the other hand, is about having multiple versions of the same method inside the same class. So one changes behavior, the other just reuses a name in different ways. All right, our final 2 pillars work together so perfectly that I like to call them the black box principle. They're all about protecting our data and, at the same time, hiding away complexity. First up is encapsulation. This is basically the process of bundling an object's data and the code that works on that data together into one single protected unit. It's kind of like building the chassis and body of a car. All the important engine parts and wires are contained inside, safe and protected from the outside world. You can't just reach in and start messing with things. And that idea leads perfectly into abstraction. So while encapsulation bundles everything up nice and tight, abstraction is what hides all that complex inner machinery. It only shows the user the essential controls they need to actually use the thing. Let's stick with our car analogy. To drive a car, all you need is the steering wheel, the pedals, and the gear shift. You absolutely do not need to understand the physics of internal combustion to get from point A to point B. That simplified interface, the part you interact with, that is abstraction. It lets us use incredibly complex systems without getting bogged down in the details. So after all that, why? Why do we go through all the trouble of designing software with these blueprints? Why does object-oriented programming matter so much in the real world? Well, the benefits are just huge. It makes the code way more logical and easier to understand, especially as projects get bigger. Inheritance, like we saw, lets us reuse code, which saves a ton of time and effort. By creating these modular objects, we can build and test different parts of a program independently. And, really importantly, encapsulation improves security by protecting our data from being accidentally or maliciously changed. It's just a smarter, safer, and way more efficient way to build software. So there you have it. That's the fundamental blueprint behind almost every major piece of software you've ever used. It's an incredibly powerful way to manage complexity and build things that are made to last. So the only question left for you is, now that you know the blueprint, what would you build?